Okay, so before we begin, I just wanted to give you guys a quick heads up on study materials you have available to you. So that practice exam was up over the weekend, but I'm sorry if you had trouble finding it. It was just under quizzes rather than linked directly under the unit. So that link is there now. I've also put up some essay style review questions here, going over as comprehensive as I can be the things I think you should know. And linked at the bottom, as usual, you got the key for it. So my comments to you about each of these questions. The other thing that I've put up that you may want to look at is, there we go. This, which is on those right and left shifts, those hemoglobin oxygen dissociation curves. So we got a picture of the curve, what these various parts of the image mean, a blank table where you can talk about each of the effects, what causes a shift, and link that up to higher and lower affinity for oxygen, higher and lower unloading at tissue, and then left shifts. And here's filled in what I mean when I say filling in the table. So if you're practicing this by filling stuff in, that's basically what I would write. So you can have that and you can practice those because I know we went through it, but working with specific examples may be helpful. Okay, so you can let me know if you have further questions on those after you take a look through, but we do have a little bit more content so that we can be done with regulation of ventilation stuff and leave our third unit entirely on the renal system. So we'll run through some more today. Okay, so last time we talked a bit about control centers in the brain and how those relate to regulating ventilation. Today we're going to talk a bit more about the receptors that are important for your body to know that it's time to change how you're breathing. Okay. So there are a couple of different kinds of receptors. We got chemoreceptors, stretch receptors in the lungs, these pulmonary stretch receptors, irritant receptors for stuff like smoke inhalation, and some muscle and joint proprioceptors, so basically sensing the size of different airways. But the main one we want to know about are those chemoreceptors. Okay. So when we say chemoreceptors, what chemicals they're receiving information about, we're really thinking about levels of oxygen and carbon dioxide, right? So we want to know, what do our gases look like? Are they at appropriate levels, right? That's why you would want to change how fast you're breathing. They are also going to react a little bit to pH. As we spoke last time, carbon dioxide essentially can get converted into hydrogen and bicarbonate ions using that enzyme carbon anhydrase. So we'll take a look at that in a second too. Okay, so you got chemoreceptors basically in two places. You've got peripheral and central chemoreceptors. The peripheral ones, the main ones we need to know about, the ones that are really important for us as humans, are the carotid bodies. They're up by the carotid sinus, so that swelling as your internal and external carotid are bifurcating, so splitting off from each other in your neck. You got that kind of carotid sinus swollen point. That's about where the carotid bodies are. So essentially, they're sensing the levels of these gases in the blood that's headed up towards your brain. Okay. And where we have our central chemoreceptors is in the brainstem itself, so on the ventral side of that medulla oblongata. Okay. So central means central nervous system. Peripheral is really saying that that's linked up to our peripheral nervous system. Okay. So the main thing we want to know about the peripheral chemoreceptors is actually this point down here at the bottom, which is that they're responding mainly to the changes in blood pH, which is really a measure of changes in carbon dioxide. And they're only going to respond to really big changes in oxygen levels. Okay. These other points, sorry, I'm trying to keep you focused on, since our exam is on Wednesday, what's the most important stuff, right? So that's the most important thing to know about them. But here we see their location here, right? So we can see them right above the carotid sinus, and we can see that they are linked up to your brain, right? So they're in contact with arterial blood down here. Then we have an afferent neuron, right? Afferent meaning going back to the brain, communicating here with those respiratory centers in the brainstem as well. Okay. So they're responding to your carbon dioxide changes via this intermediary of blood pH. Okay. So let's take a look at how ventilation changes when we see changes to our levels of oxygen and carbon dioxide. Right? Okay. So what we're looking at here, we're measuring oxygen levels as a partial pressure in the blood, right? So we're specifying, we got our arterial partial pressure of oxygen, right? And we got a curve of ranges we could be in, and we've got our minute ventilation. So how much air do we want here? How many liters per minute are we trying to breathe in here? So we know that usually we expect to see an arterial PO2, so a partial pressure of oxygen in your arteries at 100, right? That's the number we're remembering here. So hopefully you're staying at 100. Hopefully nothing is impacting how much oxygen gets into your blood, right? But we can see that if it does, right, you've got a while before you really see any changes to ventilation, right? This line's kind of flat. It's not until you get to a pretty significant drop in oxygen that the peripheral chemoreceptors would respond. Okay. But they could respond to oxygen levels dropping, which is a difference from the central chemoreceptors. So the point at which you'd start to see major changes in ventilation reacting to dropping levels of oxygen is around a partial pressure of 60. Right? So we remember we get down to a partial pressure of 40 in the veins, right? So now we're getting an arterial partial pressure of oxygen that's looking much more like that deoxygenated blood in the veins. That's bad. If you get down to 60, we're going to need to fix that. But you've got a bit of time before you get there. So usually, those peripheral chemoreceptors are responding to our carbon dioxide levels changing and therefore our pH levels changing. Okay, so our normal expected partial pressure of carbon dioxide still in an artery is at 40, right? So normally 40. As we pass by tissue, we pick some carbon dioxide up. So in a vein, it would be at 46, right? And we can see here that as soon as we start to change these carbon dioxide levels, right, as soon as they start to go up, right, we're immediately seeing a response in our minute ventilation. So we're immediately starting to breathe more deeply, starting to breathe faster as we see these carbon dioxide levels rise. Because high carbon dioxide levels are especially dangerous for your body. If they get up to about 90, right? If a partial pressure of carbon dioxide gets to 90, you're going to go into a coma. If it gets above 180, you are going to die. So your body tries to adjust this very quickly so that you don't get anywhere close to any of those numbers, right? So this is the first thing we see changing your ventilation. So if you start to change your ventilation because of a rise in carbon dioxide, right, that's probably the same time as your oxygen might be dropping, depending on what's causing it, right? But this is the primary trigger for those peripheral chemoreceptors. Okay. So the direct response that these chemoreceptors are mainly working through is in response to blood pH, but we can think of it as an overall reaction to carbon dioxide because they do respond to all three. Okay, so those are your peripheral chemoreceptors. So mostly, pretty much, we're thinking about the ones in your neck, in the carotid body. Okay. The other place we have really important chemoreceptors is in the brainstem. So our central chemoreceptors are on the ventral surface of the medulla, so ventral belly side, right? So kind of like here-ish, maybe. Okay, so these chemoreceptors are responding exclusively to changes in pH of cerebrospinal fluid. So remember, cerebrospinal fluid is that clear-ish kind of fluid that's bathing your brain, kind of cushioning it and providing it with nutrients. And it's important here because the reason that we're responsive to fewer things, if we're looking at the central chemoreceptors, is partially because we have a blood-brain barrier, right? So we have fewer things that can come into contact with our central chemoreceptors. So they are not directly responding to carbon dioxide. They're not responding at all to oxygen, okay? That said, just like for the rest of your body, right, rising levels of carbon dioxide are still really dangerous. So this reaction to pH in cerebrospinal fluid really still is an indirect response to carbon dioxide levels rising. So we can look at a picture of how this works. Okay, so what we're looking at here is we've got red blood cells going through some capillaries near your brain, right? So these are some brain capillaries. So we've got carbon dioxide, and carbon dioxide can cross into cerebrospinal fluid. So we can see this carbon dioxide going across an endothelial cell and ending up in cerebrospinal fluid, right? Hydrogen ions can't actually cross. So this means that central chemoreceptors really are only going to be responding primarily to this carbon dioxide conversion that we're about to look at, rather than to like build up of hydrogen ions in your blood due like lactic acid or other types of pH changes, right? So this is really strictly respiratory reaction. That's part of why we have this multi-step process here. Okay, so once we're in the cerebrospinal fluid, in the CSF, we can combine that carbon dioxide with some water. Water's everywhere, so we got plenty of that. Then we have our carbonic acid that dissociates, giving us those bicarbonate ions and hydrogen ions that we mentioned when we looked at the function of our carbonic anhydrase, right? So this is just naturally dissociating in this aqueous environment. Our enzyme was working here for this conversion between carbon dioxide and water. Okay, but the result is now we have hydrogen ions sitting around in our cerebral spinal fluid. We're changing the pH here of the cerebrospinal fluid a little, and that's what comes into contact with one of our receptors, right? So they're not directly touching the blood. They're not directly sampling what's in the plasma, but we've got this indirect kind of pathway that protects our brain, protects those chemoreceptors and the brainstem from things in the blood that we don't want to contact our brain, but still lets us respond to the levels of this gas. Okay, so that's what we want to know about the receptors. So our peripheral receptors can respond to everything, pH, carbon dioxide, and oxygen. We're really primarily focused on carbon dioxide levels through this intermediary of pH, is still the major reaction of peripheral chemoreceptors. But our central chemoreceptors don't respond to oxygen at all. They are still trying to measure CO2, but the only thing that they can actually touch is the hydrogen ions creating that drop in pH. Okay, so here we have our sort of flow chart that we might work through if we were trying to increase our ventilation due to a drop in oxygen and a simultaneous rise in carbon dioxide, right? So basically what we're looking at here is maybe your breathing slowed down, right? Maybe you're hypoventilating, right? You need to breathe faster so that you get enough oxygen so that you breathe off all this carbon dioxide. You don't want to pass out, go into a coma, and die, right? So we're going to try to change our ventilation, right? So in that arterial blood, those peripheral chemoreceptors, if we get low enough with the oxygen, do detect and respond to drops below 60, right? They definitely respond to carbon dioxide rising. Part of that reaction is a direct reaction to carbon dioxide. A large part of it is a reaction to the fact that rises in carbon dioxide create rises in hydrogen ions, which if we did our calculation for pH, we'd find is a drop in pH, right? So here are those peripheral chemoreceptors responding to all of that. And here's the CSF and those central chemoreceptors responding just to the carbon dioxide piece, not directly, but exclusively through that hydrogen ion and pH relationship. But overall, our big effect when we see this would be to increase ventilation, try to breathe more so that we can adjust the content of our blood to be appropriate. Okay. So hypoventilation, right? You can see here what that looks like. Summarized again, if you're not breathing enough, that's likely going to create rise in carbon dioxide, therefore rise in hydrogen ions, drop in O2. You react and breathe more. This is hopefully a negative feedback loop. Hopefully we fix the issue so this stops needing to be adjusted, in which case our chemoreceptors would stop firing. So here we see what would create a drop in ventilation, right? Because with these chemoreceptors, we can do both. So particularly with this carbon dioxide level, if we see a drop in carbon dioxide, creating a drop in hydrogen ions, would be happening often at the same time as a rise in oxygen. Chemoreceptors could respond to this. And in this case, you drop down your ventilation. So our final thing we want to understand, right? We want to know the existence of those two types of chemoreceptors and what they respond to. Then this last piece we want to know is about ventilation and perfusion, okay, and how it's controlled. Okay. So what we're trying to do with our lungs, right? We know we have this big, essentially respiratory membrane made up of all these alveoli and these alveolar sacs. So we got a lot of airflow. That's the ventilation piece. And we've got tons and tons of blood actually in our lungs. We have tons of capillaries spread all across all those alveoli coming into really close contact. We know that we only have a really thin barrier to diffusion of gases, right? Just those type 1 alveolar cells, the glued together basement membranes, and a capillary endothelial cell, right? And ideally, we want to match our breathing and our blood flow so that we are effectively using all the oxygen, delivering all the carbon dioxide in the blood into those alveoli and moving them through our bloodstream, keeping those partial pressures of oxygen and carbon dioxide in our desired range. So we have a ratio that we've created to assess whether we have the appropriate, a good amount of ventilation, matching that blood flow, which we describe as perfusion. So what we're looking at here is our ventilation perfusion ratio. So the V ventilation, right? And the Q is for perfusion. It's probably good we didn't use a P because we use P for pressures all the time, right? We needed a different letter here. So we got our airflow and we got our blood flow. Okay, so we want them to match. We want airflow and blood flow to be equal, essentially. And if they do match, right, if you divide your ventilation by your perfusion and you have equal amounts of both, right, the number we're going to be comparing to is just 1, right? So equal amounts of ventilation and perfusion. And so we're going to be thinking about what happens if this goes above 1, if this goes below 1. Like, what does that link up to if we're thinking about what's going wrong potentially with your physical body? Okay, so thinking about this ratio, ventilation on top, perfusion, which is our blood flow on the bottom, usually equal to 1. I want to see if you can predict for me what might cause a ratio of less than 1? Okay, let's take a look. Okay, great. Yeah, so that ventilation perfusion ratio, right? Ventilation, so you're breathing on top, perfusion on the bottom, right? If we're below 1, right, that means that we're dividing a smaller number by that same larger number, right? Giving us a perfusion ratio, a ventilation perfusion ratio that's lower than 1. So this is going to be caused by problems with our airflow. So probably some kind of obstruction in your airway, whether that's like an asthma attack narrowing your airway, something to do with resistance, or actually getting something physically stuck in the airway. Okay. So here we're looking at a couple of different scenarios, and we're looking at those ventilation perfusion ratios, right? So we can see our normal condition up top. We got our ventilation perfusion ratio of 1, and we can see that we're matching up our breathing, our ventilation, to our perfusion, right, our blood flow. And we can see that this creates the normal conditions we expect to see in the blood, right? So we see our partial pressure of oxygen is at 100 when we do this, right? That's what we expect to see in our arteries after we've oxygenated our blood. And we see our partial pressure of carbon dioxide at that lower level that we expect to see after we offload carbon dioxide to our atmosphere. So we're down to 40. We're at 46 as we were coming up to our alveoli, right? So this is our normal condition. And below we see what happens if we obstruct an airway in this image B, and what happens if we obstruct a blood vessel in image C, right? So what we just looked at in our sample question was that situation where we have a drop in our ventilation, keep perfusion the same, right? So we have something less than 1 here, right? So this is because we see something blocking our airway to some degree, right? It doesn't have to be completely complete, right? It might just be a change in radius, a slighter, lesser change in airflow, but we'd see this ratio below 1. Right? And now we can see that because we don't have air coming in, not as much air anyway, this is going to change those partial pressures of gases that we see in our blood as it continues back from the lungs, back to the left side of the heart, and then out through your systemic circuit. Right? So if we have this lowered airflow in the blood, you're going to end up seeing, right, low oxygen. So a lower, we can actually compare it to that number, right? So our partial pressure of oxygen is going to be less than 100 now. And our partial pressure of carbon dioxide, right? It's now building up, right? We didn't breathe out enough either, so we're now going to see something that's more than 40. Okay. So that's what happens if we block an airway. But we might have a situation where instead we're dealing with some kind of clot in one of these pulmonary capillaries, say, right? So say we block the blood flow, we have decreased perfusion, right? We're going to leave our ventilation the same. right? We have a drop in our perfusion, right? So now we're going to see a ventilation perfusion ratio of greater than 1 because we're dividing by the smaller number, right? So this is also going to have an effect on our blood gases, right? So we're going to see, in this case, with this kind of, think of it as like blood going slower maybe past this, or think of this blood here after the blockage just kind of sitting around for a little longer in contact with the air. Right? So in this case, we're going to see that our oxygen levels go up, right? Because we're putting that oxygen into less blood, essentially. So that's going to go above 100. Right? And we're getting rid of extra carbon dioxide here. Okay. All right, so we're now going to see something that potentially gets even lower than 40. Okay. So this is going to link up these ratios to what we see in terms of our blood gases. And the reason we're doing this is because we're going to see that the alveoli and these capillaries respond to the levels of oxygen and carbon dioxide we see in the blood here, okay, and in the airways, I guess. Okay. So that gets to fixing this issue, right? Because we're going to try to get back to a ventilation perfusion ratio of 1, right? So if we have a blockage, we're going to try to do something to match that ventilation to the perfusion and vice versa, right? So if we're looking at a blockage in an airway, right? So ventilation is decreasing in some of our alveoli, right? So that's that first obstruction in the airway situation with this ventilation perfusion ratio below 1, right? So this is where we see that buildup in carbon dioxide and this drop in oxygen as we have excess blood, excess perfusion compared to how much air we're getting with the ventilation. All right. So what we're going to see in response is that we are going to try to make our airway bigger, right? So if your ventilation to the alveoli is blocked, right, you have an obstruction, you have a narrowing of airways, right? The first thing you could try to do is just make the reverse change, right? So we're going to see bronchodilation, right? So making our airways bigger, lowering that resistance, increasing airflow here, right? And we're going to notice on this image, it's mainly bronchioles that are responding to carbon dioxide, right? In both these cases, right? So your airways mainly respond to the carbon dioxide levels. And we're going to see that our blood flow, that perfusion, is mainly responsive to oxygen. So each of these gases is kind of having an effect on one or the other halves of this equation. Okay. So what we're looking at, right? We looked at that decrease in our ratio being matched up to an increase in carbon dioxide, creating bronchodilation, trying to swell up that airway to get around our blockage. But the other thing we can do to get this ratio back to 1 would be to drop down our perfusion, right? If you have less ventilation to those arterioles, you could just drop down your blood flow to the, if you have less ventilation going to those alveoli, you could just drop down the blood flow to those alveoli as well. Right? So our decreasing oxygen levels that we see have a direct effect here on the arterioles, our pulmonary arterioles specifically, and they're going to constrict down that blood flow, right? So we're trying to fix this from both perspectives, the ventilation and the perfusion part, right? And if you step back, this might make sense if you think of it as like, okay, so say we totally blocked off like a bronchiole, and so all the alveoli downstream of it are getting no air, which is why we see this drop in the ventilation perfusion ratio. It's not worth it to send your blood there, right? If there's no air that's going to be able to clear carbon dioxide and give you oxygen, right? So you might as well just clamp down that blood vessel, right? And save your blood, send it to airways that actually are working. Okay. So from the perfusion side, we might also have problems, right? So we might have our ratio above 1, right? And if it's above 1, that means that we had a drop in perfusion, right? So in this case, we're going to do the same thing, right? So if we've got a blockage in our arterioles, we might just try to make that vessel bigger, right? Try to unblock it by just lowering our resistance. So oxygen is responsible for that. When we see our increased oxygen level, right, we're going to vasodilate. Okay. And if you remember when we were talking about arterioles in our last unit, don't get confused because it is true that you're seeing the opposite reaction in these pulmonary arterioles to what we saw out in the rest of the body, right? So this is different than how arterioles out in the rest of the body act when we see like active hyperemia, right? So just don't associate those two concepts, right? Different reaction here. Okay, so we can try to vasodilate to get around our perfusion issue. And if we can't get around our perfusion issue, right, we might as well not send air to somewhere we don't have moving blood, right? So these decreasing carbon dioxide levels that we see are going to trigger bronchoconstriction as well, right? So bronchoconstriction is going to shut down those airways. So then we'll get back to 1 from the other side. So we want to be able to think through this flow of the ventilation perfusion ratios. Keep in mind, right, we're trying to match these. We're trying to keep it at 1. And then we want to just be able to logically think through how we get there. Remembering carbon dioxide is leading to our reaction in bronchioles. Oxygen is creating our reactions in the capillaries. Okay. So that's all we are looking at here in this flow chart, right? So we are looking at what happens when we see changes in carbon dioxide and oxygen levels. And here we're looking at increasing carbon dioxide, decreasing oxygen levels, right? Okay. So we'll walk through, right? First, we're going to see that as we have these increasing carbon dioxide levels, especially, also maybe a little bit of this dropping oxygen, but we're really reacting here to the carbon dioxide part when we're looking at our bronchioles, right? We'd see in response a decrease in the contractile activity of our smooth muscle in the bronchioles, aka we are bronchodilating. We're loosening up the walls of those bronchioles, stretching them out, lowering our resistance as a result, right? Because we're trying to get rid of this excess carbon dioxide, really important to us. Okay. So this lowered resistance is going to increase our ventilation ideally here. So try and fix this from the breathing side. But we're also trying to fix this from the blood flow side, right? So at the same time, we are going to see our arterioles reacting primarily to these dropping oxygen levels, okay? So same thing, we're going to be acting on smooth muscle, but in this case, we're going to be increasing the contractile activity of the smooth muscle. So we're going to be clamping down that blood flow essentially. So vasoconstriction happening in the arterioles, going to those pulmonary capillaries. Okay. This increases resistance in the blood, right? So you want to note, right? This is in the blood. And this resistance is talking about in the airways. Right. So we can have resistance going down and up at the same time because we're talking about different substances. Right. So we see increasing resistance in that blood flow, leading to lowered perfusion so that we're trying to match that ratio. Again, get it back to 1. Right. So try and fix it, try and breathe better. If you can't, don't bother sending blood there. That's our like big picture takeaway for these ventilation perfusion ratios. Okay. So finally here, we've got a table just showing what the overall effect is in our bronchioles. Okay, so the airways versus our arterioles, so that blood flow, to our different levels of carbon dioxide, right, and oxygen. Okay, so you can think of it this way, study it this way instead of through that flow chart if you prefer a table form. I kind of like a table form because it's also kind of like a flashcard, but whatever works best for you, you can look at it here. So this again shows you dilation and constriction responding to carbon dioxide and oxygen, noticing that the arterioles are mainly responding to the carbon dioxide and our arterioles are mainly responding to the oxygen. Okay. So that's what we got closing out this unit. Okay. So what you should do right now is either go study in the library, have a couple minutes back to yourself, or open up some of those documents that I've shared with you, give them a look, ask any questions that you haven't wanted to ask in front of our whole lecture hall. I'll stick around for the rest of class.